All right, is the live beginning? I think so. All right, great, it's connected. Okay. Um, yeah, there was some hiccups before, so I start this, try to record this again. So, first of all, sorry that in my lab we didn't really have time to go through everything, which is why I'm making this video here. So people who didn't really catch on or have nice idea of how to do lab 2 and didn't came to other people's lab are feel free to refer to this video and also message me on either Discord or Canvas message to for any questions you have that's related or not related to this lab in particular. What we have here. So first of all, we had this as what we had before in this directory. So if I do clean to clear everything, okay. All right. So first of all, again, in our convention, we want to call if you wrote a assembly file by yourself, we want to use the capital letter S. So it's it's to differentiate it with the compiler generated assembly code, which is we usually give it small letter s, just by convention. So later on, because if you wrote this piece of assembly code yourself, it's probably important, right? You don't want to lose this information when you are exporting your project to somewhere else. However, if this code is generated from some other source code, such as the C code, and you're using the GCC or some other C compiler to translating your source code into the machine's instruction code, um, then in that case, maybe um, by keeping it small letter s, it tells you that it's safe to remove, it's safe to delete, it's safe to ignore when you are exporting your code to somewhere else, right? Because even if you get rid of that, as long as you have the compiler, you can just compile that again. But source code is like once it's gone, it's done, it's gone forever. All right, so what we have here is we have, first of all, we have sections, the data section and also the code section. Some difference between the sections, and I hope you remember this. Hope you remember this graph, which you should have seen this in 214. And if you haven't, you should remember this graph by heart in 215 because they'll be heavily used and heavily referred in our in this class. So it's the idea of the code segment or program's memory layout. So in a program, in a running program, there are a couple different, the program is also a file, it's executable file, and what this executable file really is it contains many different parts. So first of all, you have the text section, which is your codes, your instructions, and then you have your data section, which stores your file scope variables, scope your your allocated data, your arrays, your strings, right? Because string is what? String is just a character, an array of character, right? So initialize the data, which means data which have a value, such as being initialized, which means given by a value, right? You can, if you do that, you can say int y. If you have some y, you can say y equals to x. This value can be put on the right hand side, which we call the r value. So x can be the r value, which just the value on the right hand side of an assignment here. Whereas if it's uninitialized, if you have x just declared here without initialization, without definition, without initialized anywhere in your file, all this thing does and saying is that there is a symbol which is x. It's a type integer and it exists without giving any value. So then you can assume you have an integer y somewhere. You cannot say y equals to x. Why? Because x has uninitialized x cannot be our value here. All right, so those are counted as uninitialized data, and they usually be as a convention, like add something to make your life or computer's life or compiler's life easier. We're trying to group initialized data in one place and uninitialized data in another place, kind of special place, which is called BSS, which is block starting symbol. So from here, it's basically tells you that block starts from here, and there will be a dynamic place which is called a dynamic pointer, which is called heap pointer, which is after this fixed sized block start symbol, which cannot be changed, right? And if you requesting more memory during the runtime, which means you are calling the malloc or free, this heap is what you can use to control the memory. It's what you can use into controlling it. It's by controlling the heap. When you call malloc, it's you getting more space on the heap. If you call it free, you move the pointer back. It's actually in the operating system implementation, it's most likely to be as a linked list, but we don't care about this stuff in this course. But in the operating system class, the idea of using linked list is better to be a double linked list to designing your heap, designing your malloc, your program space, your with memory structure. It's really helpful. Think about that. And yeah, so what does the block starting section really is? For now, I can just say it's it's read-only data. That's where things placed, and yeah. So read-only data is by saying this part, any symbol in here can only be read as access mode and cannot be using write, cannot be modified. If you're trying to modify it, your operating system will give you a sig file because you're trying to think it's sig file or sig int or other. I think it's probably a sig file. Can't remember, but the idea is you can use telling the operating system to catch you if you're trying to writing anything here, such as a string, fixed literal string. You shouldn't be modified in the runtime, so you put that section here. You can, though, after this point, you can say section dot data, and you say, integer x. You say this is a dot word, initialized to 8. Then it's initialized data with the value of 8 with the size of a single word. So you can do something like that, of course. So then what's in this pane of the screen here is I trying to so first of all, if I run make, it's gonna make the let me stop deleting file. Wait. What is let's take a look at the make file. Alright, so makefile, I just define this toolchain path and toolchain's prefix. For if you're doing your lab, if you see the error, right? As someone who's in the program of computer science, if you see an error, such as this first thing you need to do is trying to make sense of the error, trying to understand, because error is great thing. Error is what tells you what goes wrong, right? It has information in all kinds of errors. And instead of just, oh, this code doesn't work, it's broken, I can't fix it, nothing to do, it's maybe there is a bug. But you, as a computer science student, as a future computer scientist in this program of computing science, you need to read the bug. If you think there is a bug, locating it, try to fix it. And yes, you can do that. So by trying to making sense of what's going on here, you kind of read, read output line by line, and this is what they're trying to do, and this second line is what says the error is. It says cannot find no such file or directory. What file is not existing? Well, it says there is no file that's in user local risk of multi bi, which is named binrscv64-un. There's no such file named. Does this file name strike you as particularly strange? If yes, right? Definitely there isn't such file. Like if you go to this path here, if you go to this path here, if you do ls, do you have a file that is called binriscv? No. There is a bin, yes, and if you go to the bin, you do ls. Yes, there are risk v, your toolchain stuff, but why doesn't it put a slide? Why doesn't it put a slash? Computers are doing everything that you exactly as how you're instructing it to do. The reason for there isn't a slash is because you never put a slash. So, right? Because see, this toolchain is trying to call this toolchain and its assembler. And this toolchain literally says the toolchain equals to the toolchain path plus the toolchain prefix. And the toolchain path is this thing ends with bin, ends with letter n. And the toolchain prefix is starting with r. So the n will be followed by this n will be followed by this letter r immediately, right? This is basic string concatenation, and I don't think any of you have trouble with that. Just adding a more slash, that's make it work. And then a kind of stuck here. And this way. One moment. So I'll again makefile if you can remember what makefile does. So makefile is a recurse, so it's defining the recipes and rules of the building process and trying to automating it recursively, which means if you require this hello, it's trying to run hello because the first rule is called all, it's trying to do all. And all requires hello, and so hello will be called. And hello requires this object file, which is hello.o. So before it's doing this process, it says, oh, I need to do this first. So just kind of like, you're cooking, right? You say, I want to make a soup. All right. So the soup, I need the diced potato and diced carrot. Do I have diced carrot? No. So then I'm looking for the recipe to make a diced carrot, which means I need knife and carrot. And once I cut this recipe, this target, so this is a recipe, which means your target is the diced carrot. Your prerequisite, well, you would have a cutting board, you would have a knife, you would have a carrot, right? And then the recipe it's what you're gonna do with those prerequisites, with your tools, with whatever you already have. Is you can say cut the carrot with the knife, and it's going to satisfy the requirement for having a diced carrot. And once you have the diced carrot, if you also has the diced potato prepared already, you can go ahead, make the soup, and it's going to produce the soup, which is going to be satisfied by the first rule. Default rule is the first rule. You can think that as just today's dinner, which is kind of abstract, right? But once it's satisfied, it's done, which means you have the dinner. You have your dinner, which is your carrot and potato soup. Now I need to see why this doesn't work. Right? Why does this keep going? Oh yeah, because I didn't give the flags. That's right, it's wrong. Sorry. Yeah, so we don't do GCC directly because GCC is a compiler. It's the compiler that what the compiler does is it's translating the machine language into translating the source code file, which is your C file, into machine instructions. But if we are coding machine instruction, right, the compilation step is not needed. All you need is something called assembler and also linker, which assembler is I won't say it's translating, but it's more like direct mapping. Hope you guys will learn that in fairly quickly already learned that each instruction will be can be represented by an opcode, and so each instruction is also can be represented by a 32-bit value, such as if I have add A5, A7, A5, A3, right? This can be translated into a 32-bit binary number, which can also be represented by some hexadecimal number. And again, this is not accurate. I just give a random hexadecimal number. But another thing we want to looking at is the compilation. It's called compilation steps. So it goes through a couple of 4 steps, basically pre-processing, which is the string. What I think is just string copy and paste, right? If you see hashtag include, it copy and paste everything from the include file into your code. If you see a copy and paste, if you see a macro definition, it just copies the macro definition into where it refers to that macro. So those are the pre-processing. Compiling is what translates your source code into the machine's instruction, and then assembling well formatted into this machine's digital format that can just can be put in a file that's your object file, and then with this object file and few other things, and by the linker is going to link everything into an executable, which means the computer will looking at the file, the first line will be a instruction, and it just keep going through the instruction to executing all those instructions. So if we try to do a right, so this is the assembly flag. It's a couple things we need to get on. So flag. So special settings to telling it is a 32. So this is specifying the architecture we're using and also the platform or ABIs we're using. The linker also has flags, so LD flag 32. Now if we say make, it's stuck here. Let's see. Interrupt. Oh wait, sorry. This one didn't give the. I didn't give the. It's waiting for my input, of course. Well, because it's right. I didn't give the input here, so it's thought the input well coming from the string, but it didn't. So once I have that, let's say hello. Hello. Let's make again. Oh. Wait, illegal operand. I. Okay, so what did I do? So this could be money. So there are if you know, try to find things that helps your understanding, help your learning, and sometimes you do have to go outside the of whatever the classroom gives you. And yeah, I think percentage I and percent L, that's how we do that. So there are a lot other places to looking at those menus by risk V. Those it requires more time, but if it helps you understanding, it's great. Yeah. Anyways, sure, just fix that and change it to a normal load address way. And define a reference to a string, of course. It's called hello string, that's why. Right, so when the code is not working, the first thing you're trying to do is to what? To trying to fix it. So you can either change the variable's name or change your reference name. I did this just because it's faster. Okay, illegal operands. So this produces the object code, and then using object code, it produces this binary code. So if you really want to read the object code to see what the object code has, we're using a tool which is called objdump. And you can just give it, if you don't, right, it tells you which flags to pass, but I think you can just do capital letter D for the symbol O, and you say hello.o, and I'll just put this output to the Vim so it's easier for me to navigating. So this is the object code after the assemble process. After the assemble process. And right, it's almost same as what I have here, excepting. So again, as I mentioned before, this will be this machine's instruction that's represented as an integer or as a hexadecimal number. Assembler will do the replacement, will translate this, because this is still a text file if you think that way, right? This file is actually like machine cannot directly executing this .s file. Why? Because it's just a bunch of letters. It's a dot, it's a letter E, it's a letter Q, it's a letter U, it's a space, it's a capital letter S, capital letter Y, capital letter S, right? So the assembler is processing all this information and translating that, not really translating, I won't call it translating, it's more like a direct mapping it onto a those digital representation for this like 32-bit number representation of this instruction. And LA, such as load address, which is a pseudo instruction, is translating this pseudo instruction into some other instruction that the machine can actually, do the job. And yeah, and calling that and the load immediate, this will be the same. And ecal, this will also be the same, which telling the operating system to go. The string, string sys string. Right. So this is the data section, which is hello world. And luckily or unluckily, somehow our string, a part of the string. So again, object dump is like it understand it trying to put the address on the left, it puts the hex representation on the second column, and trying to make sense those values as a instruction. So I think it's a jump instruction. If you interpret that as instruction, yes, it's actually a jump instruction, but it makes no sense. Why? Because it could just be letter O space W. Yeah, it could just be a, okay. So this is letter H, the letter E, L, L, letter O. Yes, oh, sorry. H, E, L, L, letter O, space, capital letter W, lower letter O. So those are actually, strings. It just happens that it also is same as the instruction for this jump instruction, which this instruction would make no sense. This will be some default settings for the RISC-V. Again, those are just data. So one takeaway, and I'll mention this more times in class, and I think you should become more aware of that, is data is data. What does this one mean? Well, no matter what's your data, right? Integer, float, string, instruction, those are just data. What is data? It's just a bunch of zeros and ones, which can be represented as a string, can be interpreted as a string, can be interpreted as a float, can be interpreted as a string, as a character, as a instruction, right? It's just different forms of the same thing. All right, so yeah, that's not the point of this lab. So first of all, I think we need to go back to review the makefile. The point is just telling you how to use an LD to link things into the binary, and also using the assembler to mapping it. So this is the first part, and then the second part is trying to using GDB to work through your your code and looking at the code basically. So GDB, hope you have used it in 214 before. However, first of all, how to execute in our program. I think on the lab's specification, you are supposed to writing a bash script to do that, as a automating process. For my demo here, I'll just type that in bash, because bash script is basically your command one line at a time. That helps you. You can regenerating it at any time as you wish. So I can say QE new 15. I can define this bash variable. Say this is student CMPT215 QE new. So my bash is kind of slow every time it goes to the /student. So do student /CMPT215. Yes. Right. So QEMU. I think this one has it already. So BIN is and QEMU. So BIN icon. No. So try to echo this QEMU 15. This variable will contain this path, right? So then if I say QEMU215 slash, it's okay to have multiple slashes. It's okay, but it's not okay to not having slashes. It's QEMU-RISC-V32. That's our 32-bit RISC-V emulator, which is kind of like a virtual computer, a small computer inside your computer that's trying to operating on those RISC-V architecture instructions, right? We're trying to using it to run this hello, and it prints hello world, and it leaves. So GDB is trying to debugging. If you're using GDB, it's it debugs executable code programs on your computer. However, is this program really being executed on your computer? Like, can I do, right? It doesn't work that way. It's not running on your or on this Tax World computer. Then which computer is running? It's actually running on the QEMU, right? So the GDB is not only trying to debugging it. So in order to debugging with the GDB, we need to have a few more steps. So first of all, the QEMU has support for GDB natively, and you just need to give a -G option, and it says to a port number, and I recommend using port number that's quite random and greater than 35,000, and I think it's less than 65,000, something like that, but starting with greater than 35,000, that should be enough. If you find your port is blocked, you just try another random number. It's recommended to use your last 3 digits of your INSET because it's less likely that we would have a collage in that case. So you say -G, which means forwarding or allowing control through this port number, and then you're running this little computer, this little RISC-V computer on this program on this port, right? And now this is okay. It's not like it's it's crashed or anything. It's just waiting for things to happen. So now what you need to do is trying to open another terminal. It's really easy if you have a TMUX, which is a terminal multiplexer. I strongly recommend people begin to picking up TMUX and picking up Ling from now on is going to be extremely helpful. As you can see, I can have different buffers opening different files and checking different stuff, and still like within one terminal. If I need another window, it's like I can always have another window. Right? You can have multiple panes opening there. So on the other terminal, you say again we have to use the special slash student. No, sorry. Our 2 chain. Your GDB is also part of the this 2 chain. So user local. Alright, so I say 2 chain pass. I say that equals to user RISC-V multi VN, and then I say 2 chain pass, and I say RISC-V. RISC-V64 unknown elf GDB. That's our or even I can do something else. I say that 2 chain pref equals to elf dash, and then I say 2 chain pref GDB Yeah, so to do that, you have to have a bracket. Right now, that code. It's directly string concatenation, so you it's kind of so to chain pref, I said that GDB and hello. Alright, do that. Alright, so now so GDB to open this binary file, and now it says reading symbols from hello. If you do start, it won't start. It says do not know how to run because it's not running on this computer, right? The host, you see, this is like cross-platform debugging with your host to be this x86 computer, this TaxWord computer, and the target to be the RISC-V architecture. You're trying to do the architecture. So target, you're trying to connect to the remote target. You say target, remote, and this asks you to provide a file. Could be any, again, if you take operating system class 332, you alert everything is a file. So for now, we say the file or the socket, this location, the port is existing on localhost 35228. That's the port number I get there. So then it's begin debugging. It says reading symbols from here, and it begins doing the debugging process, which is great. So right, if you do next, single stepping until from function, right? Oh, sorry. Yeah. By doing next, it's like going through. If you say n next line, which means going through the entire function or the first procedure, and the parent procedure right now is underscore start, so it won't go into the start. It'll just skip over the start. Therefore, it finished. So to do that again, forwarding it, giving control to this port, and you say target, remote, localhost, everything here, and now, oh yeah, oh I spelled things wrong. It's localhost. And so you say SI to step in. So now this is inside step. So N. Since didn't really go into zero, so okay. Yes, SI. Right, you say this is like doing this step, and it calls hello world on that line. But you can't really see which line it's going, right? You can see the locations. It's increasing by 4, which means it's next instruction. But you can't really tell which instruction it's doing. So what I would like you guys to do, I would like you guys to picking up, is to using the TUI mode, which is the text interface mode. So to enter the TUI mode, it's Control X and then release X. You say A. No, Control X. A. Yeah, you're going to the TUI mode. Control X A. You go out. To make it more helpful, TUI mode support up to 2 split screens. So you say Control X, and in the number, type number 2. So now this mode is enabling to have 2 sections displaying on here. So you say layout. Why did it say assembly is available? Oh, sorry, yeah. So currently this target cannot be debugged. Why? Because I didn't include any debugging symbols. You should in this this is wrong. In this assembling stage, you say -G here. So here, this make it able to be, it's an object code that supports debugging. So now if I run make again, and now Let's run the this port. Trying to hello, and if I say target remote localhost. Yeah, okay, it's great. So now it's actually reading those, reading this symbol. So step in, next line, and before it's doing the eval, if you want to examine, so using the p command, which means print. So p $A0, you can see the value stored in this register, right? It's not helpful, not really helpful to seeing that as a integer. So if you do p/x, it's trying to render this as interpreting this as a memory address. And if you want to see what's in A7, you say A7, it's 2048. And next line is going to do the eval, which is our print string system call. So after this, you can see hello world has been printed out. And you keep going, exit, and you say the process or program has exited normally. So in that, yeah, so here, if we connecting to it again, let's say target remote, connecting to it, and then go to the TUI mode with two split screens. So Control X, press number 2. You can see this is assembly code. So again, do not remember to, do not trying to memorize everything, but trying to memorize, not memorize, but learn the ways to finding resources. So GDB TUI mode. There are many different places you can pull up your resources, references online for anything, basically. So layout, there are basically 3 sections you can looking at. It's layout, will be source, assembly, and register. So right now you're looking at the assembly, which is .object code. Right? If you want to see your source code, you see layout src, this will be your source code. And you say layout reach, this will be register values once you have them ready. So, which means if I begin to step in, now everything has been initialized and you can see the registers. And if I say, and again, if you do the same operation, like still keep stepping, which means going through, keep going through, you don't have to type SI again. You can just say enter, which repeats the previous command. So now this one has loaded the value into register A0. Has loaded the value into register A0. And A0, as you can see here, it has, if looking at it in the hexadecimal way, it's 10090. As an integer, it's 65680. This is the address. If you want to know that what is in the address, using a command which is called gdb's x command, which is a command trying to display the memory content, right? So x, the value of A0, or you say x, the value, you can actually put the memory address on there. So what we see here is what we can see here is, I'll just make it smaller, hope you can see on your screen. I hope so. So what we can see here is, this is just a hexadecimal, 32-bit hexadecimal representation of some integer. Is not helpful at all, right? Or is it? So let's see what this integer really is. So 65, so 0x, 6c, 6c, 6548. So first of all, when we're looking at binary numbers or hexadecimal numbers, just numbers, right? Where do we begin to read it? Like, where is its first byte? Maybe. Are we coming from left or are we coming from right? So we should start in reading it from here, right? Because this is a bit 0. this it's a bit 32, right? It's like the bit at this location is a bit 32. It's the highest bit. So when we say the memory location at this address, this location, it really means this byte, and then the next byte is this byte, and the next byte is 6C, and next byte is this byte. So the if we're trying to, so byte 0 be 48, byte 1. So if I say byte 1 would be 65, byte 2 would be 6C, byte 3 be 6C. But what this byte really means, right? Those are just like, are they just numbers? Well, they kind of not just numbers. If we're looking at using calculator, I should be using that. There is a way to convert hex to decimals. Section. Oh, int is a base. That's great. All right, so Python is I'm using Python more like a tool in this case. So basically, if I have, so I say int, if we are interested in what is this 48 really is, so we say 48 base 16 is 72, right? And what this really is you can put this number into the char. It return you the CHR. It's going to return you the character that's represented by this number. And again, I think in 214 you all learned that all letters, characters are just a 128 bit, it's just a 8-bit integer, right? Like letter H is represented by hexadecimal 48 or decimal integer 72. So we can do, so let's read another. So next one will be 65. So let's say 65 is 16, which is E. And I think you can figure that out. Is next letter will be L, next letter will be L, right, and then will be O. So this is one way to looking at the memory. It's just trying to looking at the bit patterns. But again and again, data is data, right? A data can have many different representations, even though the content is exactly the same, right? Are just representations of this stream of bits. So it doesn't hurt to, which format, which representation you choose. It's really depending on which one you're more comfortable with. So again, to looking at the X command, actually have options here. So not only you can just say address expression, you can also say give a slash, which means a format, and you give a format, specify which format you want to go with. So you say format, read it as an instruction, read it as a string, read it as a character, read it as an address, right? So if I say x/a $a0, so this is rendering that as an address, which is kind of just like hexadecimal values. If I say x/a binary, yeah. So x/t a0, this will be the binary representation for this same value. It's again different representation. If we interested in the character, well, you say this is h, right? Well, so where are the other characters? So again, this means just reading one byte from there. So if you want to see the next byte, you just say A0 plus 1. It's the next letter. And plus 2 is the next letter, right? And then we see there is another option, is that giving a length and a format and after. So, well, that means how many characters you want to keep reading. If I say 10 characters, so this means from A0, reading character by character by character, and reading 10 such characters. And as you can see here, it's HELLO space WORL. That's the, if you're reading 10 characters. And you can /s to interpreting that as a string directly. And when it's as a string, there is actually a backward /0 in the end, which is telling it where to end, where to terminate, right? It's telling it where to terminate, and it terminated. So it stops after the /n. That's so yeah, so basically, so to getting out of the TUI mode, again, Control XA to go in again. So those are things that I think this lab 2 really should be talks about. Again, it's, I would say, learning is much more really depending on yourself, because computer science is so deep that if you don't do any extra readings, it's okay for you to pass the class, but you won't have as much of the learning experience, the ways to figure out how to figure out something, and the skills, the experiences, those are what's really important. It's not just, oh, I know how to do RISC-V assembly code. No, it's your understanding of the computer's architecture, how to, the experiences with debugging codes. That's the learning outcome that you should be looking forward to. Again, if you want to show the registers content, you can say P, but I guess in the TUI mode, you can quite easily to see. And also, when you put out the layout bridge, right, you can see there is highlighted sections, which means if some value has been changed, you can see that it's highlighted, it's been highlighted. Right, A7 is the most recent change, so it's highlighted here. And I think that should be it. Any questions? Again, you can shoot me a Canvas message and shoot me a Discord message. All right. See ya.